My name is Lars Folkerts from the University of Delaware, and I'm presenting REDsec, running encrypted discretized neural network in seconds. So we have built out a fully homomorphic encryption framework, and this framework is usable by everyone in this room, where you could just plug and play your neural network and have an encrypted output. And we'll go through, starting from the very beginning, what fully homomorphic encryption is, then our cool techniques that we use to speed up our framework, and then finally, how to use our framework. So the problem we're looking to solve is machine learning as a service. So you have, as it is today, a user and the AI cloud. Now the user is going to have their input to the neural network, and they want to keep this input top secret. So what they could do today is they could encrypt it with AES or a similar encryption scheme and send it over to the AI cloud. Now the AI cloud cannot do anything with this data. In order to do anything, they have to have the decryption key and decrypt this input. And when they do that, this violates the privacy of the user. So now the cloud could take the user's data, use it for advertising or whatever metrics they want to use it for. But they need to do this in order to process it and get the results. So with traditional cryptography, privacy is violated because you're giving the cloud your personal data in order to process. With homomorphic cryptography, it's possible to do computations on encrypted data though. So if you have a basic equation that you want to do, say 5 + 2, you could encrypt these as polynomial ciphertext and send them to the cloud. The cloud could run an encrypted addition on these. So this is not a standard addition, it is a complex polynomial operation. And then they'll send back that ciphertext, and when the user decrypts it, it is 7. So in the encrypted domain, we could run these operations that parallel what we're doing in plaintext. So you could do this for addition, and then you could also do it for multiplication. And when we put this all together, what you're left with is you can build a full neural network out of this application, right? So that's what homomorphic encryption is. And then here are the challenges that we have with it. So traditionally, you can only do these shallow problems in the neural networks. If you have too many operations that you're running, you won't be able to decrypt these ciphertexts. Now, there is a way around it, but this way is slow, as I'm sure you guys have heard. So it's getting much faster. It's improving kind of like a Moore's law trajectory of 10 times faster on year across different encryption schemes and benchmarks. So 4 years ago, they ran ImageNet on AlexNet, and it ran in an extrapolated time of 833 days. We run in a couple hours, in 1.6 hours, the same benchmark. So it's 12,000 times faster than that NeurIPS 2019 paper, and it's only 4 years later. We're seeing huge leaps and bounds in this field, and there's new breakthroughs coming through every couple months. And then finally, in order to use homomorphic encryption, you have to really learn the different parameters and stuff. So this is another challenge we're overcoming. So our framework is going to tackle all these challenges, and we're going to go through exactly how. So our approach for how we get our speed ups, we're going to use the TFHE library, which is an encryption library for homomorphic encryption. And we're going to combine that with the LARC neural network code. That's how to train our discretized neural networks in the plain text. And we build this all together in a framework so you guys could easily use it. So the features in TFHE that we exploit for our speed up is we're going to use these binary ciphertexts. These are encrypted bits. They're either encrypted 0 or encrypted 1. And these are great in discretized neural networks for activations and multiplications. TFHE also has integer ciphertexts. So these are standard integers, and these are going to be great for additions. So previous work has focused either on the binary ciphertext, which have really slow additions, because you have to run these full adder circuits. And then the more recent work has done integer ciphertext only. Our work is going to bridge the two. So we're going to switch back and forth between binary ciphertext and integer ciphertext so we get the best of both worlds. So the highlights of our work is we maintain the privacy, and we run at the 128 bits of security, the current security standard. We're able to run deep problems, and we run AlexNet on ImageNet. We are fast with our bridging technique and the other optimizations, which we're going to go through. And then we have our bring your own network framework, which has both multi-CPU and GPU support. So this bring your own network framework, if you want to use it to develop your cloud application, you can come up with your neural network idea, and then you start using the tool that we developed. There's a visual tool that will help generate a net list of all different layers you want. So you put in here the layer dimensions, the input sizes, and all that. And then we have a code generator that will output the LARC training code for you. It's a TensorFlow-based library. From there, you're going to train your neural network, get the TensorFlow weights. Our optimization has a weight converter module to optimize the weights for the encrypted domain. Our code generator will also give you the inference code. And then you're going to deploy the optimized weights and inference code onto your AI cloud. So now we can run the machine learning as a service model, but encrypted. So you have your AI cloud and you have a user. And this user has their inputs, but now they can encrypt it with fully homomorphic encryption. Because they sent it to the cloud now, and now they know that there's no way the cloud can decrypt this. So now your cloud can run their algorithm in the encrypted domain and send back the result to the user. And then the user, and only the user, can decrypt the message. So you can't get any of the user's information. So let's go into some of the details of fully homomorphic encryption. So when we encrypt, we take these plain texts and convert them into these very large polynomial ciphertexts. And then we're going to add a little bit of noise to guarantee the security. This is random Gaussian noise, and it makes sure that your ciphertext cannot be broken. So this noise is great for adding the security, but it's going to bound the computation. So as you do more operations, noise will accumulate. So if you look at the thermometer on the right-hand side, when you do an addition, the noise will go up a little bit. And when you do a multiplication, the noise is going to go up a lot. And you're going to accumulate. And once you reach a certain threshold, the noise will become too high. And when you decrypt, you're just going to get garbage. It's going to be random noise. Luckily, there's a process called bootstrapping to bring down that noise. So when you do bootstrapping, noise is going to reset back to the beginning. So this bootstrapping procedure is great because you don't have to run only shallow neural networks. You can run these deep neural networks and keep on refreshing this noise level, but it has high latency. In some schemes, they don't implement bootstrapping at all in their libraries because the latency is so high. With TFHE, it's manageable. It's on the scale of milliseconds. So we're actually able to run these deep neural networks with bootstrapping. REDsec takes this a bit further, and we're going to bootstrap only when needed. So what we do is we take, the naive way of doing things is that you're going to bootstrap after every operation. And it's up to the programmer to kind of tune it themselves and figure out where to remove the unnecessary bootstraps. We do that for you automatically. So we're going to measure the noise growth the first time we run the neural network and pinpoint exactly where you need a bootstrap. And then future iterations of running it, we know exactly where to insert those bootstraps, and we'll do that for you. And this leads to a 32 times speed up over the naive implementation. All right, so now some basics of discretized neural networks. So this is in the plaintext domain, just kind of how they operate. So they have convolution and fully connected layers, which are a bunch of multiply adds, and the multipliers are with weights of -1, 0, and +1. Second operation is the sign activation function. So here, anything that's negative becomes -1. Anything that's positive is going to be +1. And then the second nonlinearization function is the ReLU. So this is a max of 0 in itself. So anything less than 0 becomes 0. Anything greater than 0 is itself. And then with discretized neural networks, you have to discretize it every layer. Otherwise, the precision is going to grow out of control. So now when we move this to an encrypted domain, here's where we get our speed up. So for the convolution and fully connected layers, we have an efficient multiplication scheme that uses a NOT gate instead of the 2-input XNOR gate. And because it's a single input NOT gate, it's more efficient than homomorphically than the 2-input XNOR. And then we take care of the rest of the multiplication inside the bridging technique. And we needed this bridging technique to move back to the integer domain, where we could do the efficient integer additions. Now, bridging is not a free operation. It costs a bootstrap. So we want to avoid it as much as possible. So instead of bootstrapping after every multiplication, we came up with a way to reuse the data so that you don't have to do that, and you can only bootstrap for a limited portion of the data. So this data reuse and preventing too many bridgings is actually what makes this bridging technique effective. Next up, the sign activation. We're going to first add in some bias, and this is the bias is for batch norm, so we do support batch norm. Then we're going to bridge over to the binary domain. And then finally, once we're in the binary domain, we have a bunch of bit ciphertext. We just grab the sign bit. It's super simple. So we use a different mapping where 0 is a negative number and 1's a positive number, but pretty much you just grab that sign bit. And then finally, for ReLU, what we do is it's a complex operation. So you can't really compare and say if this is greater, if this is less than 0 because it's encrypted. So some schemes use lookup tables, which suffer from precision problems. We have a different approach. So we'll first apply the bias in the integer domain. Now we have to multiply it because we care about magnitude, and then we add in some bias as well for the batch norm layer. Then we're going to bridge back to the binary domain. And then here, we could use the AND gate with the sign bit. Because we're in the binary domain, this becomes very efficient. So again, 0 represents a negative number. Anything end with 0 is 0. We get our ReLU. All right, let's talk about a little bit more of our other optimizations. We have a multi-GPU acceleration on CUDA. So we have a separate library that does this called cuFHE as part of this paper. And it can be general purpose as well. And there's lots of parallelism we have to exploit here. So within a neural network itself, there's lots of parallelism, right? You're doing a lot of operations parallel. But then within each operation itself, there's FHE level parallelism. So that multiplication is not a simple multiplication, it's a complex polynomial operation. So there's lots of speed up. And our framework takes advantage of both these levels for the most optimal parallelization. Additionally, we're highly scalable. We have a dynamic scheduler to assign tasks to GPUs. And then we limit the number of memory transfers optimized for the neural network application. So summary of our contributions. We have the efficient multiplication with a single input gate. We have the bidirectional bridging to take advantage of binary and integer ciphertext whenever the most efficient implementation is. We have the integer addition with this data reuse to prevent too much bridging. And then we have the binary activation functions. And then we package this all together in that bring your own network framework with the noise auto tuning to make it super simple for you guys to use. The GPU acceleration, and the high scalability, we're able to go to AlexNet on ImageNet. So for the results, we compare with MNIST because that's what other works do. So we run this in 3.6 seconds, and compared to that 4 years ago, that's 3,000 times faster. CFAR10, we also are able to run, and we run that in the scale of minutes, 3.8 minutes. That's 11,000 times faster than the fully homomorphic implementation 4 years ago. And then finally, we have the binary AlexNet, which runs in 1.6 hours. So we're making huge leaps and bounds in the field as a whole, and then our work further accelerates this. And we're the first one with an actual fully homomorphic ImageNet AlexNet implementation to run that benchmark. So here's a more direct comparison of the works. So we're the pink over there. And in the blue, that's the binary ciphertext only domain. So here, again, you have those full adder circuits, which are not really efficient. So you have a scale of hours for just running MNIST. The more recent works have used integer ciphertext, which are more efficient and comparable to ours, but we scale much better than those integer ciphertext only implementations. So when you get to a modest size 1024 input, 1024 output neuron network, all the way on the left, we are about twice as fast as an integer ciphertext only. And then when we directly compare to our related work, so here we show a Pareto frontier. We're up there on the upper left. So we're higher accuracy, it's higher up, and then lower latency further to the left than the competing works. So we have feed-in and concrete a little below us. Those are integer ciphertext implementations. And concrete suffers from a problem in its programmable bootstrapping that prevents high precision. So that's why you see the accuracy drop off as the neural networks get deeper. And then we have TOPUS, which is a binary ciphertext implementation, and that's on the scale of hours, and that's way up the charts. That was kind of the old way of doing things. right? And then GPU, we see more of the same. So that's us. Again, we're either more accurate or faster than the concrete implementation. So if you guys are curious, here's the QR code to our GitHub and our link. And if you're interested in any collaborations in fully homomorphic or other privacy encryption technologies, please reach out. My email is on the slide. And any questions, link them now.
I was wondering regarding the applications of your, like how many models can you use to verify the homomorphic encryption algorithm that you have proposed and the framework that you have proposed? Like, did you try to use, for example, one short-term memory networks? What's the effect of homomorphic encryption on sequential information? How to discretize it? For example, if you want to use transformers, very deep hierarchical neural networks, what is the effect of your framework for this kind of exhaust?
So our framework is sequential neural networks, and we focus on image classification for benchmarks. So we're looking at other ways to enhance it and adapt it. So we're looking into stuff like transformers, homomorphic as upcoming projects. So we're going to keep on working and building out some of these technologies.
So mainly, if I need, just check here, framework on GitHub, I can create any kind of algorithm and use it.
Yeah, so you get to build your own network.
All right. Okay, thank you.
Okay. Any other question?
So we're going to post the recording of this later. I want you to patch a demo with that as well. The trails are written out on that.
There is no other question. So maybe I ask. You can finish on. Okay. So let me, one thing is not asked here to me. So you have specific neural network, and then you applied all for encryption or fully on encryption. So it's a specific class of neural networks. And for image, just all right.
Yeah, so we focus on it's so easy for us to carry without really getting too much of machine learning. But we need things like transformers and stuff is all fascinating applications.
You guys with the number of parameters going up to several billions. What do you do? How do you do it? I mean, is that any concept where this is a GPU scale? So are you scalable also to parameters which are huge from the perspective of the
parameter size and foot size? Yeah, so the cyberattacks are pretty big. All of encryption, it is 2.2 kilobytes attacks. So there's a lot of stuff you have to do with memory transfers and like ImageNet helps.
So then the contribution of this was the breaching, or was there, you did touch the homomorphic. We use the typical flow of encryption libraries that exist.
Yeah, so the novelty, we have more detail here. So the breaching is kind of what the main indicator there. There's a lot going behind the scenes to enable that.
So what is this more kind of the challenge line in the implementation, engineering?
So the challenge is trying to find, well, the implementation itself, right? The challenge itself is finding most efficient ways to run it at a standard level. And then there's a lot more it can use to get everything.
Well,
so combination of both having the breaching is now the techniques you're trying out and became that I think suite has their own networks and a lot of handling of scale.
copying that.